Let's use the method of Lagrange multipliers to find the dimensions of the right circular cylinder of maximum volume that can be inscribed inside a sphere of radius 16. Okay, so I drew my XYZ axis and I drew a sphere of radius 16. And I want you to kind of think of it like a spherical apple. And then what you're going to do is you're going to core out a cylinder, right? Like an apple core, right? You're going to take a cylinder out of the center. And so what we want to know is what's the maximum volume of that cylinder. So that's our objective function. Our objective function is volume equals, and that's a cylinder, so that's a known formula from geometry class a long time ago. It's pi r squared h. All right, so that's some function of r and h. No problem. Okay, so what about our constraint? Well, it's inscribed inside a sphere, kind of like a big old round apple, right? It's inscribed in there, inscribed inside a sphere. So let's make a constraint. I'm not going to do it in red, though. That would be very hard to look at. All right, so constraint function. Well, we know it's inside, inscribed inside, a sphere of radius 16. Okay, spheres are a known quantity. We know how they look. They're x squared plus y squared plus z squared equal to 16 squared. Now, we need to do a little bit of fancy footwork here because this is no good for us. We have our objective function in terms of radius and height, but we have our constraint function in terms of x, y, and z, and these variables are not matching. So, warning, right? The variables don't match, and they have to. Okay. So, I mean, technically we could do this either way, but it's going to be easier to mess with the constraint function here. So, first off, how do x squared and y squared relate to the radius? Well, if you remember from polar coordinates, x squared plus y squared is r squared. We learned that definition with polar coordinates. So that's r squared. Half our work is done, right? So r squared plus something else squared. Now this is where we need to do a little bit of looking at our diagram here. Okay, that's the z. Now the z is from here to here. That's z. But z is also from here to here. So the height of the cylinder is 2 of those z's. Let me do it in orange here. So the height is 2z. So in other words, z is the height divided by 2, right? It's the full height cut in half. So that's what we'll use over here, height divided by 2, right? So since height is 2z, then height divided by 2 would be 1z. And now the variables match. Now they're both in terms of r and h, and they only have 2 of them, not 3 of them and 2 of them. That's no good either, right? They gotta have the same number. You can have 3 as long as they both have 3, right? Okay, so now we're ready to go with our Lagrange multiplier, sort of. The only other thing is that the constraint function must be equal to 0, and this is not equal to 0. So our constraint function, g of, and it's not going to be x and y, I was about to write x and y, but g is actually in r and h. That would be r squared plus h squared over 4, right, just distributing that, minus, and this is 256 equals 0. Right? Your constraint function must equal 0. And now we're ready to go to set up the Lagrange multiplier. So let's set up Lagrange multiplier. We know that the gradient of the volume is equal to lambda times the gradient of the constraint. Okay, so that would be VR. I'm just going to write it here. VR VH equals lambda times GR GH. VR is the derivative of this with respect to R. So that would be 2 pi RH. The derivative of volume with respect to H would be pi R squared equals lambda times the derivative of this constraint function with respect to R is 2R, and with respect to H, the 2 would come down, so it would be H over 2. All right, so now let's set up our equations. So this first piece, this piece is equal to this piece. So 2 pi RH equals lambda times 2R. Therefore, lambda is 2 pi RH over 2R, which is just pi h. Actually, the pi is, yeah, to pi h. And then the other component gets us, let's see here, pi r squared equals lambda times h over 2. So lambda equals 2 pi r squared over h. And then we just put the two of them in maple and make maple solve. All right, so let's go to maple. You can see I actually drew the red sphere. Right, there it is in all its glory. And then there's the volume, there's the constraint function, there's the gradients of them. Okay, so right here. So I'm saying, hey, 2 pi RH over 2R, I didn't even bother to make it pi h, even though that's what it is, equals pi r squared over h over 2, right? And so I solved that for r, and I got r is equal to square root of 2h over 2. I could have solved it for h. I mean, it doesn't really make any difference. All right, so I got, and the negative, of course, is irrelevant, right? We're not going to the negative radius, so it doesn't make any difference. So square root of 2h over 2. So r equals square root of 2 over 2 times h. That's what we're seeing. All right, so we did that with maple. Now, use the constraint function to find values. Okay, so in the constraint function, it was r squared, but we're going to put this in instead. So we're going to say, hey, take the square root of 2 over 2h, square it, plus h squared over 4 minus 256 equals 0, and we're going to solve it, right? So I'm taking this function that was r and h, and I'm using the fact that r is equal to the square root of 2 over 2 times h. I'm going to solve this for h, right? Solve with maple. And let's see what we got. All right, so I said, hey, evaluate. I first did an evaluation. I'm like, take this square root of 2 over 2h and plug it into that equation for that constraint equation for r. And that got me this function. And then I said, set that equal to 0 and solve it for h. And I get 32 square root of 3 over 3. Again, the negative is irrelevant. You can't have a negative height of a cylinder anyway. So we're going to do 32 square root of 3 over 3. And I didn't give any units. So let's pretend this was inches, just for example, right? I didn't give one, but pretend. It could be centimeters, it could be whatever. All right, so 32 square root of 3 over 3, right? We know the height. We know one of the values. All we need is the radius, and we're good. But remember that the radius is equal to square root of 2 over 2h. So the radius is the square root of 2 over 2h, and so radius is the square root of 2 over 2 times 32 square root of 3 over 3. We're just going to plug in, right? Plug in that value. 32 square root of 3 over 3, and find a way, right? So that's 32 square root of 6 over 6. And again, this would be inches or it could be millimeters. I didn't specify, but it would be some unit of length because radius and height are both lengths. And just for fun, I threw that into Maple as well. I had to do a simplify command because it did not like doing this. It multiplied square root of 2 times square root of 3. So I had to put in simplify in order to get it to come up with this. Oh, and that is the right answer. I didn't think about it, but of course 32 and 6 are both divisible by 2. So that would be 16 over the square root of 16 square root of 6 over 3 inches. Here, I'll circle that one. And I'll uncircle the other one, even though they're both correct. It's just the one on top is not fully reduced because 32 and 6 are both even numbers. So they're both divisible by 2. There we go. And notice again with the Lagrange multiplier method, we don't have to check any of the answers. We know that this answer is automatically optimized. So as long as we did everything correctly, which we did. So we don't have to we don't have to check it. We don't have to stick it back in, make a table or anything. None of that stuff. The only thing is that you'll have to make sure a couple things, that you have the same variables and they line up, right? So R and H or X, Y, Z, like pick a set and go with it. And then you also have to make sure that your constraint function is equal to 0 in order to make this work. But as long as you do that, you use Maple to help you solve things along the way, you'll be all set.